Jai Hind. The topic which we are going to cover today is functional dependencies in Dbms. Functional dependencies, that is FDs. We will see what is the meaning of the FD, how and why they are important in Dbms. In connection with FDs, one more concept we are going to discuss today in this lecture, that is to find the closure of a FD or to find the closure of an attribute. So, before proceeding towards the definition of the functional dependency, we are aware that the primary goal of database design is to decide what tables we need to create, and while we are creating the tables in our database tables, that is the relations which we are creating in our database, it generally work on two principles. Number one is it should capture all the information that need to be there in our database. Also, it should achieve this above concept with minimum redundancy. Redundancy should be minimum. While keeping this redundancy to a minimum level, the main objective is to capture all the information, that is the relation schema which we are going to design. It should contain all the attributes, all the values which we want to be present in our application. The first principle, that is this one, is enforced basically with the ER diagram which we have earlier seen in the previous lectures, and the second with the normalization concept. So, the FDs which we are going to discuss, that is what is FD, and that is in connection with the normalization. What is the definition of FD? It says that it is of the form X tends to Y, that is it is known as X imply Y, where X and Y, they are my attributes. It means that whenever two tuples are identical on all the attributes in X, they must also be identical on the attributes in Y. What it implies? That, for example, I am having two attributes X and Y. Let's suppose X is having the values A, B, C, then again A and B. And corresponding to A, we are having here 1, 2, 3. Then if this is identical here, then the value of Y in both the case should be same. Similarly, these two values, they are same in attribute X. So here it should also be 2. If we are having some other values here, for instance, here I am having 1 and 2, but here I am having, let's suppose, 10 and 12. Then in that case, X implies Y would fail. So, alternatively, we can interpret that if X imply Y, then it says each possible values of X can correspond to exactly one value of Y. That is, if X and Y attributes, they are represented with some finite set, and if I am having this value corresponding to this, then this value never corresponding to this if X implies Y. So, functional dependencies are generally the constraints that are required by the underlying application, and that is why we need functional dependencies in our schema. This is the formal definition of the functional dependency, that is, let R be a relation schema where alpha and beta are my attributes, and the functional dependency, that is alpha imply B, holds on R if and only if for any legal relations R, which is corresponding to capital R, whenever any two tuples T1 and T2 of R agree on the attributes alpha, they also agree on the attributes beta. That is, if these two tuples, they are same in alpha, then their corresponding values in beta should also be same. And this is what we have discussed here. Here the left hand side is known as determinant and right hand side is known as determined. That is, alpha in this case becomes my determinant and beta, it becomes determined. Let's suppose it is my relation where this is my alpha, this is my A and this is my B attribute. Then on this instance, B imply A holds. How? That is, both these values, they are unique. And in that case, if I says this is B and this is A, here I am having 4, 5, 7 and here I am having 1 and 3, then 4 uniquely corresponding to 1, 5 to 1 and 7 to 3. So this condition hold. But if we look at the reverse part, that is, here we are having A, that is A is acting as determinant. Here B is acting as a determinant. Here we want to check when A is determinant and B is determined. So whether this particular FD follows or not. So here what we are doing? So here 1, 1, 3 and 4, 5, 7. So if you look here, this is in contradiction to what we have discussed here. So this particular FD does not exist. Assume, let's see a few more examples. Following FDs hold, that is CID implies title to department. Then these two FDs, they corresponds to these two, that is department and CID. Year corresponds to CID and department. So we need to see whether the following tuples coexist or not. Then in that case, let's check for the first one, that is CID2. Title, so CID here C1, same and corresponding to same beta. Here the C2 it corresponds, so this will follow. Title to department, that is title here and department database. So this will create a problem. Then CID and year, both are the, department. It is department. And this is year. So here title and department, that is title database. Now 3 database and we are having 2 values of beta. So again it won't exist. So we can see for the rest one also. What about the following? Agar we are having CID C1 and department is in this case is C, then in that case CID to department does not exist in that case. Types of the functional dependencies, generally we are having 2 types. One is trivial functional dependencies and the another one is non-trivial. What's the trivial functional dependency says? It says a functional dependency where X implies Y is said to be trivial if and only if your Y, it is the proper subset of X. Thus, if right hand side of a functional dependency is a subset of left hand side, then it is called the trivial functional dependency. So these are the example here. This is my right hand side and this is my left hand side. Here what we are having, this is my left hand side and this is my right hand side. So what we are having? We are having right hand side, it is the proper subset of my left hand side. So in this case, these are the examples of my trivial dependency. Non-trivial, it is just the opposite of the trivial, that is a functional dependency where x imply y is said to be non-trivial if and only if y is not the subset of x. Thus, if there exists at least one attribute in the right hand side, that is here, that is not the part of left hand side, then it is a non-trivial. That is here, if we see B is a part of left hand side, but C is not the part of left hand side. So in this case, it is a non-trivial functional dependency. Again here, CD, none of the attribute in the right hand side is the part of left hand side. So again, it is a best example for the non-trivial functional dependency. These are the inference rules or the Armstrong's axioms generally we use for finding out the new FDs in our schema, or to find the candidate key, or to find the closure of a FD or the attributes. These are the three main axioms. Number one is reflexivity. Reflexivity, it says x imply y for any y is the subset of x. Augmentation, it says if x imply y and if we add attribute at both left hand side and right hand side, then this also holds true. Transitivity, it says if x imply y and y implies z, then indirectly x also implies z. So this is the transitivity rule. Closure of a set of functional dependencies. What is the definition? Given a set of functional dependencies, there are certain other functional dependencies that are logically implied by f. That is, we are given a relation, and on this relation we are given few FDs, and if we are able to generate more FDs with the already given set of FDs with the help of inference rules, then we can say the subset, the set, the newly formed set, it becomes the closure of a set of functional dependencies. So here, if A imply by B and B implies C, then we can infer A implies C. So if they are a part of my FD set, then this automatically will become a part of my FD set. So the set of all functional dependencies which is logically implied by F, that is F is my FD set, is the closure of F, and it is denoted by F on the and we are having plus sign as the superscript. This is the closure of attribute. Just like your closure of a set of functional dependencies, we are having the closure of attributes. Closure of attributes, what it says, let alpha be the set of attributes in relation schema R which is determined by alpha under a set of F of functional dependencies is the closure of alpha under F, and it is basically denoted by alpha plus. That is, alpha is my attribute. Here what is happening? F is my functional dependency set and here alpha is my attribute. How we compute the alpha, that is the closure of an attribute? First, we initialize the result with alpha and we do the task in the repetition. For each functional dependency, beta, sorry this is missing, beta tends to gamma. In F, what we do, if beta is the subset of the result, then the result become the union of gamma. That is, if we are, suppose we are having, we are having attributes, let's suppose A, B, C and D, and I need to find the closure of attribute A, and I am having some attribute FDs, for example X tends to Y, then AB tends to C, and I am having, this does not exist, then C tends to D, then suppose we are having another attribute E tends to B and so on. So here if I need to find out the closure of A, then in that case we will look in all the FDs, and if we find where the beta is the subset of result, that is beta here, that is your left hand side. If that is the subset of my result, then my right hand side, it becomes the part of result. Let's suppose I am having here A to E. So if here what first result, it becomes A, then A, this particular FD, it follows this condition. So here result, in the next step, result becomes A and E, and so on. We go on, we repeat this process until we are not able to further include any attribute in our closure set. So let's start with an example. Here we are having a relation schema R, A, B, C, and we are having two FDs in this case, and we need to compute closure of attribute A, closure of attribute B, and the closure of attribute C. So let's start with finding the closure of attribute A. So what's the first part says? First part says that result is equals to alpha. So in this case, result is equals to A. Then for each functional dependency, we need to check this condition. So here, this is my result part. So what will happen? This FD, it is suitable for this criteria. So in that case, my new result set, it becomes AB. Why? Because A imply B, result includes the B in that case. Now we go further on. Now look at this FD. B is the subset of this result part. So what will happen? So B implies C. So now C becomes the part of my result. So the closure of my attribute A, in this case, it becomes A, B, C. Now look for B plus. So here result is equals to B. Now this FD, it satisfies my condition under the loop. So now my result, it becomes B union C, that is BC. Now if I go for this further does not satisfy this result part. A is not the subset of my BC. So in that case, the closure of B, it becomes BC. Let's suppose find out for C. So here the result part becomes C in this case, and if I look at these two FDs, we are not able to include any right hand side part of my FD in this result set. So in this case, the closure of C attribute is the attribute C itself. So this is how we find out the closure of the attributes. So this is, we have seen in the previous slide, closure of beta, B plus is BC, and closure of C is my attribute C. This is another example. Here what I am having the relation. Moreover, you need to remember that in this case, if I try to find out the F plus, then in that case A implies B, B implies C. So with the help of transitivity rule, in this case, if I go with the transitivity rule, then in this case A implies C, but it cannot be used to find the closure of attributes. But yes, if I need to find the closure of my F, that is this part, then it comprises of these two plus this one. So here A implies B, BC implies DE, and AG implies D. Let's compute for the attribute AC. closure, we need to find out the closure of AC. So initially my result is AC, then A is the subset of this. So new result becomes ABC. Here what we are having, I am having BC, and here I am having BC. So BC is the subset of ABC. So new becomes DE. Okay. So this is the new result. Now look, go here, AEG. G is not the part of my result, and that is why we cannot use this FD to include more elements in my closure set. So here the closure of AC, it becomes A, B, C, D, E. This is how we generate the closure of attributes. Closure of functional dependencies. In this case, we are having, we have already seen reflexive, augmentation and transitivity rule. And in addition to these three rules, we are having three more rules. One is union rule, decomposition rule and pseudo transitivity rule. These rules, they are also very important, because when we go to find the canonical cover, then these three, in addition to the previous one, that is the Armstrong axioms, they become very important. So what's the union rule says? Union rule says if alpha implies beta and alpha implies gamma, that is left hand side is same but right hand side is different, then we can combine the right hand side, that is beta and gamma. We can combine these two attributes. It is also important to note that if we are having, let's suppose beta tends to alpha and gamma tends to alpha, then union cannot be applied on the left hand side. You always apply union on the right hand side. Decomposition rule, it says if I am having alpha implies beta gamma, that is on the right hand side I am having two attributes, then I can break this FD into two. One is alpha to beta and another one is alpha to gamma. If you look here, that if these two FDs exist, then we can infer this FD with the help of the union rule. So in the union rule, we are clubbing together the elements on the right hand side, whereas in the decomposition rule, we are breaking down the attributes in the right hand side. Now what's the pseudo transitivity says? That if alpha to beta holds, then we can have alpha to beta to that is delta holds. That is, we are having two FDs. In these FDs, what is alpha to beta and gamma beta to delta. In pseudo transitivity, what we have seen, if alpha to beta and beta to delta exist, then we have said that alpha to delta exist. This we have seen in the transitivity. So what the pseudo transitivity says? Pseudo transitivity says that we are having alpha to beta, but in this FD, we are having an additional element present in the left hand side, that is gamma. If such kind of scenario is happening, then we can combine this and this here. That is, we can have this particular FD. So here, this is my pseudo transitivity rule. Now, what is the procedure for computing closure of functional dependency? We have already seen an example. To compute the closure of a set of functional dependencies F, first we initialize the F plus with the F, that is, we have already seen here that in this case, that is F initially it becomes this, and with the help of these two FDs, we are generating new FDs and keeping them in the attribute set. Functional dependency set. So for each functional dependency, F in F plus, apply reflexivity and augmentation rules on F, add the resulting functional dependencies to the F. Similarly, for each pair of functional dependencies, if F1 and F2 can be combined using transitivity, then add the resulting functional dependency to F. What it says here, I am having the reflexivity and augmentation rule, and in this, for every pair, I am checking for the transitivity or the pseudo-transitivity rule. So with the help of these two rules, if I am able to find new FDs, then I will include those new FDs in my FD set. And this becomes at the end, when I am no further able to include more FDs in my F plus, then this becomes my final answer. For example, I am having a relation schema A with the attributes A, B, C, G, H, I, and here I am having these FDs. So here in this case, some of the members of F closure, it could be I am having A to H. How I have come to A to H? With the help of these two FDs. So this is a new FD with the help of the transitivity rule. I had find out. Then AG to I, how I had find out? By augmenting A to C with G to get AG to CG. That is AG to CG, that is here. And here after this CG to H, so new it becomes, that is AG to H, as well as another one is AG to I. So I could have this thing. So this is how you will find new FDs in my FD set. Keys and functional dependencies. K is a super key for a relation schema R if and only if such kind of FD exists in my system, that is K implies R. That is all the attributes in my R. K is a candidate key for R if and only if K implies R, but no attribute of K can independently imply R. What it means? Suppose my K, it combines of two attributes A and B. So I am having K imply R. So if such kind of dependency exists, suppose K implies R, also A implies R, then K can never become the candidate key. Functional dependencies allow us to express constraints that cannot be expressed using superkeys. For example, in this schema, I am having a table for the schema. In department, I am having ID, name, salary, department name, building and budget. So we expect these functional dependencies to hold. In this, we can clearly find out these dependencies, that building is dependent on department name, and building is also dependent on my department ID. But we cannot hold that salary is dependent on department name. In this relation schema, you cannot find out this, but maybe this kind of dependency is hidden and it is existing. If I try to find out the F plus, then in that case, it becomes the part of my F plus. So this is all about for functional dependencies. In the next lecture, we will discuss how to find out the candidate keys in my schema with the help of FDs, and how to find out the canonical cover. Thank you and Jai Hind. These are the references which I have used for making my slides, and you can use these these references for studying further on this particular concept. Thank you and Jai Hind.